Hello, this morning I'd like to see how many things I can do at once. Namely, I'm going to be trying to edit a LaTeX document today while I work on my video this morning. I just watched part 1 of my Gaussian curvature videos, and it brought to mind a sort of vision where I should build some arbitrary curve and imagine spheres or oblates moving around the surface, changing shape to fit the curve as they move around. There's sort of a list of known unknowns that came to me while watching the videos. There's sort of a list of known unknowns that came to me while watching the video, the first video. I've been focusing in particularly on the Wikipedia article on differential geometry of surfaces. So I gave the definition of the Gaussian curvature K as RT minus S squared divided by 1 plus P squared plus Q squared. And RT, S, and P and Q are defined as the second derivatives or first derivatives of f, where f was a surface, was basically just a function of x and y. And the Gauss normal map was n of x, y, and then there actually is no z in this formula, but they did express it as a function of x, y, z in Wikipedia. The Gauss mean curvature is defined K sub m equals et plus gr plus or minus 2fs divided by 1 plus p squared plus q squared squared. They don't give the definition for e, g, and f in the Wikipedia article though. But we do know that K sub m is 1/2 kappa 1 plus kappa 2, whereas K is kappa 1 times kappa 2. So I'd like to come up with a derivation of the Gauss map or Gauss normal map, if I can. I want to know how to find the two principal curvatures, kappa 1 and kappa 2. I wonder how it is that the Gaussian curvature K is a product of the two principal curvatures, kappa 1, kappa 2. I wondered if I can engineer K sub m, reverse engineer K sub m to find out what E, G, and F are. Does the Gaussian curvature represent where to place a sphere to fit into the curvature? It might have to be some kind of oblong thing. Okay, it looks like I've just discovered another, maybe possibly a better representation for my purposes of solving what K is. And this is under the actual article Gaussian curvature, whereas I got the other formulas from another page. But again, this uses E and G and F, calling that determinant 1. This says Gaussian curvature can be expressed as the ratio of the determinants of the second and the first fundamental forms. And then it gives these letters ln minus m squared over eg minus f squared. This may or may not refer to the E, G, and F in the other thing. I also have something here that refers to a Hessian matrix, and what's kind of neat about this is that in this particular form, I have no questions about anything there. I don't think. I'm assuming this is the... Oh, yes, I do. Nabla F is going to be, nabla X will be del x of F plus del y of F. Or not, no, it wouldn't. It would be del x of F, comma, del y sub F, comma, del z F, if, that's kind of a good question, um, is this in there? And if so, why? Because f is not a function of z, so I would think this would be 0. Or, since f equals z, could say that's 1. Maybe that's 1. I'm not sure. Since Yeah, maybe it's 1. All right, so what does this notation over here represent? I'm thinking nabla f is this thing right here. Nabla f transposed is this thing right here. And h of f must be this thing in here. So that would make sense. It's a little difference though, because I have been thinking f equals z. This is a little bit of a different expression. We've got f of x comma y comma z equals 0. So f of x comma, wait, how do I write that? Okay, what I would do is instead of writing f of x comma y comma z equals x squared plus y squared, I would write x squared plus y squared minus z equals 0. That is what, and then this, instead of writing x squared plus y squared equals z, um, and then I would write equals f of x comma y. Actually, this one doesn't have the z in it, and this one does. So that helps. Okay, so here is the equation from the Wikipedia article. Here I've kind of adjusted it for, or drawn it up in LaTeX. So here's something I notice is that this order is a little bit ambiguously defined. Um, well, I'm not sure. I actually don't know for sure if there's an example of this, but are there examples where uh, del f, del squared f, del x, del y is not equal to del squared f, del y, del x? I'm not 100% sure whether that happens or not, but if it does, then the ordering here of whether you're doing the first of del of these cross terms may be important. And yeah, in fact, anytime you've got a situation with a curl, then this is going to be negative of each other. But I guess maybe in situations where we're talking about gravity, there is no curl, so you can make those both equal to 0. But generally, these would be equal to the opposite of each other. So essentially, this is what we've got, that we have an alternative Gaussian curvature formula. The K is the determinant of a matrix composed of I think they said this was the Hessian, which is these three terms right here, and then this term coming down, this term coming to the right, and then a 0. And all of that is divided by the length of the um, gradient of f squared. And it should be noted that here we aren't defining z as, or we aren't defining capital F as the surface. Rather, we're defining z as the surface, and f is sort of like the 0 function. I don't know exactly what to call it. But it is a function of x, y, and z, which is the surface minus z equals 0. It's going to be 0 all the time, which gives me an idea of what to do here as our fourth thing in the list is, instead of taking a derivative with respect to any variable, it's going to be a non-derivative, a how do I say a non-derivative? How about identity? And then I'll go ahead and point out that f is 0 here, and then I'll just put id for identity. XYZ identity. XYZ identity. And then coming down, XYZ identity, XYZ identity, XYZ identity. So it would make more sense to put identity twice, the identity of f. And you know what? So long as we're putting nabla f being identity of the identity, let's go ahead and put plus or minus f squared in there. I don't know, since we actually have never used this sign of the identity. Yeah, in any case, I don't know what sign we necessarily is used here, but it is 0, so it doesn't really matter. So I'll actually just put plus 0 squared in there to remember that that 0 would actually be in the nabla of f if f is defined, I don't know. Yeah, I have no idea if nabla f should include the f identity or not, but regardless of whether it is included or not, we are going to state that it is 0. It seems like in all of these places where identity is, though, it might be of some interest to stick in something like del f del t, that would indicate like a movement of the surface over time or something like that, rather than just say. But I'm not sure that this form would necessarily, how do you say, be conducive to that idea. I think probably not, come to think of it, because if f were a function of time, if the surface f of x comma y were a function of time, we'd have z equals y comma t, and f would be f y comma t minus z. Then del f del z, or del f del t, if z was a constant in time, then del f del t would be still 0. Del f del t, that would have the effect of zeroing here if you actually did a derivative with respect to, well, no. No, it wouldn't. No, it wouldn't, because you're just going through the list. You're going del f del x, del f del y, del f del z. Oh, but no, you would be adding a del f del x, del f del y, del z, del t right here. So you don't want to do a derivative with respect to time there. All right, I think I'm going to take a break now. Maybe when I come back to it later, I'll actually plug this thing into Mathematica and see what